Thanks so much for sticking around for the very last session of I.O. and the last session in our Daydream series of talks here at I.O. 2016. It's really fun to be here to talk about Daydream and to talk about it in detail. Today we're going to talk about building high-performance Daydream apps. So, as I'm sure you all know, Daydream is Google's new VR platform for building immersive, interactive, long-form VR applications and experiences. And when we talk about creating immersive VR, creating a sense of presence, really what we're doing is creating an illusion for the mind, albeit an extremely compelling illusion. And today we're going to get to the APIs for how we create that illusion. But before we get there, we need to understand why this matters from a physiological level. So there's two very interrelated and important systems to understand when you think about presence in VR. The first is your inner ear, your vestibular system. This is the part of your body that understands balance, that is what responds to like when you tilt your head, when you move your body. That the system has a constant sense of where your head is oriented in space. The other system is your ocular system, your eyes, which of course are how you see the world. And normally, unless you've eaten something you shouldn't have, those two systems are perfectly in sync with one another, right? As you move your head, your eyes adjust and your inner ear picks up the change right away. The challenge is that in VR, there's actually a lot of things that happen between your movement, which is instantaneously sensed by your vestibular system, and what your eyes see, right? You have things like when you move your head, there's sensors in the phone that have to pick up that movement. They send that to the CPU, which does computation and simulation. It renders, it sends that to the GPU, which does rendering, and then the display has to output it, and then finally it gets to your eyes. And the longer the gap is between, what the movement that you created when your inner ear sensed and what you see on screen, we call that motion to photon latency, the amount of time from motion to photon. And that's responsible for how present we feel in VR. And the more, a lot of lag, we feel very absent. In fact, you can even feel simulator sickness. And so really our goal and what Daydream allows is for you to get below 20 milliseconds of motion to photon latency. And the focus of today's talk is how you do that and how you do it in a sustained fashion. There's another thing that I think is really important, which is at a higher level. We're all building experiences. When we talk about mobile VR, these are devices that run on batteries. They're 7-watt devices. But we're also in a world full of computers that plug into power plants, right? The 600-watt devices. And of course, we want to create immersive, compelling, fun, engaging experiences for mobile VR that feel just as good as the ones you can get on high-end desktops. So to do that, Daydream provides a platform for you, right? There's a hardware component to the platform, the phone itself, all the Daydream certified components in it. And then there's the OS, Android N and its VR mode, support for low latency rendering and head tracking and all of that good stuff. So to tell you how to take advantage of that hardware and software platform, we're going to look at 3 really key components. We're going to look at rendering, how you actually set the machine up to get it to run in the low latency mode, general performance and optimization strategies, and lastly, how you can use audio to save yourself a lot of time and your phone a lot of energy. So the first and really key section is rendering. This is where a lot of time and compute goes in VR. So let's say you start with a Daydream phone, right? Great. In a simple version of rendering, you're like, I have a phone, and then I render to the phone screen. Like, that's our ideal. Like, I have a thing, and I render to it. Done. But the reality is that rendering doesn't work that way. It's more complicated, right? So, traditionally 3D apps are double buffered. You render to one, image or texture while the phone is scanning out another texture. But because there are 2 buffers, that buffering adds latency, right? It takes a certain amount of time to scan one while you're rendering to the other. And so already you may have 16 or 30 milliseconds just from that one step. And in fact, on Android, by default, not in VR mode, it may add another frame or maybe even 2 frames of additional latency as Android tries to smooth out the experience. And this latency, which isn't noticeable at all on a regular app or game, is very noticeable in VR. And so our goal is actually in VR to get back to that original idea of basically you render a frame and it's instantly available on the screen. Ideally, we want 0 motion to photon latency. So in the section I'm about to go through, I have a bunch of code, all of which is extracted from samples, part of our new NDK. I'm focusing on C++ here because I think that's what most folks are going to be interested in. There are Java examples as well. The short link at the bottom is for the source code if you want to follow along and look at the unexpanded source. In this section, I've kind of cropped out the interesting bits and left out some of the boilerplate, which is important but not as material for this conversation. So one of the most basic things is setup. This is in your main activity.java file. You have your onCreate for your activity. And the first thing you want to do is create a GVR layout, which is a part of our SDK. And the GVR layout includes all of the scaffolding for core UX and UI in Daydream. And it also is what's going to give us access to an internal pointer that we use in the native code in just a little bit. You want to create a GL surface view, standard way of rendering to GL in Android. And then after that, you're going to want to actually set a renderer up, a native renderer for your surface view. And when you do that, there's two really important functions. The first is on surface created, and you're going to want to use a JNI method to get from that Java function into your native code. In this case, I've got a simple sort of mock C++ function called initializeGL. And this is what's going to be called from that on surface created. The first thing you want to do is using this API pointer, which you can get out of your GVR layout. You say GVR API initializeGL. That kind of tells us, OK, Daydream SDK, we're about to get started. From there, the next thing you want to do is say, hey, GVR API, get recommended render target size. And what's interesting is what that's going to do is it's going to look at the phone that the user is using, and it's going to look at the optical properties of the viewer that they're using and compute an optimal texture size such that you get 1-to-1 pixel precision at the center of the lens. Then you're going to need to create a new frame buffer, or frame buffer chain, really, by calling our off-screen frame buffer handle function, calling create to it, and then passing in the render size. Now, that render size is actually mutable intentionally. The recommended size is not the only size you have to use. You may decide to use higher resolution or lower resolution frame buffers. But the important thing to highlight here is that we're creating an off-screen texture. We're not rendering directly to the front buffer. We're rendering an off-screen texture. And this off-screen texture is actually larger than the physical display of the phone. And we'll talk about why that is in a few more slides. So going back to our main activity on Java, now that we've set everything up, the next most important function is onDrawFrame. And this is the tick function. This is the heartbeat that was going to pump our renderer and keep us drawing at 60 or 30 hertz. So here now we're back to C++. Again, we use a JNI method to get into C++ for drawFrame. And at the top of the function, you want to take that frame buffer handle that you got in your initializeGL function and call setActive. You're telling, again, our SDK, all right, we're ready to go. Like, we're about to start drawing using the resources that we've allocated for you. Once you do that, you need to get the head pose. And the cool thing is that you use our API, you say just, hey, get where the user's head position is. And you're automatically accessing all of the low latency sensor data, all of the sensor fusion, head tracking, all that's in there. You don't have to worry about it. It's one line of code. We do tons of work for you. And now you know the orientation of the user's head. The next step is to draw the left and right eyes. I've omitted the details of that code, but basically you're going to draw the left eye to the left side of the image, the right eye to the right side, and now you have, hey, stereo rendering. Pretty awesome. Once you've done that rendering, you need to do a couple more steps before it's really ready for VR. The first is just calling set default frame buffer active, yeah, that's right, set default frame buffer active, and that's, again, we're sort of saying, okay, like we bound this thing, we rendered to it, again, SDK, we're about to push it out to the screen. And then you call distort off-screen frame buffer to screen. You're saying, okay, like I made an off-screen frame buffer, I rendered to it, now distort it, which means do lens correction. If you're not familiar with that idea, it's basically when you view a virtual world through lenses, really you're looking at a screen that's just inches from your eyes, but you feel like you're looking out on an entire virtual space. The virtual view distance is different than the physical view distance, and it's lenses that make that possible. But those same lenses that let you see the screen and feel like you're looking on a world warp the image. And so we actually have to do a counter distortion, which is based on the optical properties of the lens, so that you don't see all straight lines looking curved through the lenses. So this distort off-screen frame buffer is going to take care of that lens distortion for us using the undistorted perspective that we've provided. So we have our stereo screen. That winds up getting distorted, and if you actually look at your screen, you'll see it's kind of vignetted and warped as we've done this barrel distortion on it. And then we're going to want to do one more thing here, which is there's a technique that we use called async reprojection, where if you think about what's happened, where you got called get head pose, and then you did some rendering, and then we said, hey, GPU, go do this thing. Some time has elapsed. It may be only milliseconds that have elapsed, but probably their heads have moved a little bit more just in the time it took you to render both of those eyes. And so what we do as part of our distortion and presentation pass is we take your scene and we shift it just a little bit more. At the last possible second, we get the very latest head position and warp again. And that way, it further reduces the sense of latency that users feel as they're looking around the world. And then finally, with that shifted and corrected, reprojected view, we push that to the scene, and that's what you see on your phone. Except, actually not quite, we're not quite done yet. So the other thing that's really important is that if we just naively took that view and rendered it to the screen, you would get tearing, because the screen is actually refreshing. There's, it's being rescanned over and over and over again. If you have a single block of memory that's being scanned, and you just sort of write blindly into that block of memory, you're going to see ripping on the screen. You'll overwrite maybe part of the screen as it's being updated. And it's really unsettling, especially in VR. So in order to update the scene right away, but do it without tearing, we have to enable a feature called scanline racing. And what scanline racing does is we know exactly where the scanline is in the display, and we make sure that we update right behind it so that it kind of looks like this. But basically, we make sure that we're updating slices of the display just in time for them to be scanned out. And when you get all that timing exactly right, you have the minimum latency that allows you to draw directly to the front buffer. And that's kind of cool, I think. I really like this animation. It's fun. It's like so many programmer hours to make that, animated GIF a reality. So there's a couple more things that you need to do. Like basically what we just talked about, that gives you the fundamentals of low latency rendering in Daydream. But we're not quite done. And if you just did the previous, some things wouldn't quite work. So back to Java, there's another function that you need to call, which is set VR mode enabled. And what this is basically saying, hey, Android OS, turn on VR mode. And when you do that, some really important things happen. The whole Android N VR mode stack comes alive. A lot of functions turn on or allow you to turn them on because you've said, okay, we're in VR mode. And it's even a cue for things like, oh, notifications should no longer be rendered in mono. They need to be rendered in stereo because we're telling the machine that the user's now in VR. Also, the Daydream controller is it requires that VR mode flag. So if you want input, you have to be like, hey, I'm in VR. Otherwise, we won't talk to the controller and waste battery on it. So the last thing is you want to enable sustained performance mode. And it's really one of the other challenges of smartphone VR is that we're not just trying to do low latency rendering, we're trying to do it in a sustained fashion, in a way that works on a phone, for minutes, tens of minutes, hours at a time. And what sustained performance mode does is it actually manages the hardware. If you're not familiar with the details of how phone hardware is designed, most phone interactions are very bursty. The phone's in your pocket, it's not doing much, just waiting for a call. Then you pull it out, you unlock it, you check your email, you browse the web, and then you put it away. And so the phone wants to kind of turn on and go burst, when you launch your web browser, and then back off again. Well, for VR, we actually want to run, we're running really hard, right? Like this is sustained stereo, 60 hertz rendering. But if the phone was allowed to run at its peak speed, it would actually generate more heat than the phone can dissipate. And so sustained performance mode tells the OS, hey, manage your CPU and GPU a little bit differently, run at a lower peak speed in order to maintain your throughput for a longer period of time. Last thing you need to do is in your Android manifest.xml, there's two tags. The first is the VR mode tag, and the second is the VR high performance tag. VR mode is a permission. You're saying, hey, I need to be able to have access to VR mode in my app. And then the high performance, it says, it's basically like, I am a Daydream app. Like I can take advantage of the Daydream API. And both of these can be required either, you can set this required flag to either true or false. If you set it to false, it means that maybe I'm actually like also a traditional app with a Daydream mode in a self-contained VR environment. So I don't require Daydream for my app to be installed, but I'll benefit from it if it is. However, you're saying, no, I'm building a Daydream-only app, and I only want this to be available to users with Daydream-ready phones. You want to set that high-performance tag to true. You're saying, I require this to exist for my app to run. So a lot of you are probably thinking that's great, like all this C++, I'm glad that I understand it, but I don't do that. I use game engines. And that's why we're doing native integrations with both Unity and Unreal, the two most popular game engines for VR development. And what these native integrations actually are using the same NDK that you have access to, and actually incorporating most of those same functions I've just shared with you, but into these large professional code bases, and making sure that it's bubbled up through the ecosystem and settings and all of that. So if you're a Unity developer, we have a plugin available right now, but it doesn't take advantage of all of the Daydream optimizations. That won't happen until the native integration this summer. For Unreal, that native integration is available right now in the 4.12 developer preview. So I want to talk more broadly about performance, things that you want to be thinking about whether you're writing your own engine or using a game engine that's commercially available. So when we talk about performance, there's a tendency to think mostly about like polygons and pixels, to be like, is my character too high polygon? But the thing you actually need to think most about when you're talking about performance on smartphones is thermals, is heat. Like I said, your phone is capable of producing more heat than it can dissipate if it runs at its absolute maximum speed. And phone SoCs are designed that if they ever generate too much heat, they'll actually throttle themselves back. They'll slow down. In fact, they'll slow down a lot. They'll hit the brakes to cool down enough that they can then speed back up again. And if you're in VR, you don't want that to happen, right? You don't want to be running at one frame rate and then slow way down and then come back. Like it's like sitting in a car that's speeding up and slowing down, right? We want smooth, steady frame rate. And that's much more a function of thermals than of like raw pixel count or polygon count. The other thing to think about is recognizing that both the CPU and the GPU generate heat, as does all of the interconnects between them, system memory, all of that stuff. And the CPU and the GPU are on the same die. They're very close to one another. So if you're generating a lot of heat from the CPU, that will affect the thermal budget available to the GPU. Similarly, if you optimize things on the GPU, it'll make the whole system cooler. So remember that you're thinking through a self-contained package, and it's a whole ecosystem that you're optimizing for and thinking about the thermal profile of, not these sort of like abstract and interdependent parts, though you might think about them on a console or a desktop PC. One of the most basic optimizations on the CPU side that you should be thinking about are batch counts, or what some people call draw calls. Every 3D object in your scene has to be processed by the CPU, handed off to the driver in order for the GPU to render it. And that, of course, takes work. It takes compute, and sometimes quite a bit of work to prep that geometry and send it down. In fact, when you profile a lot of VR apps, one of the most common bottlenecks is that they're CPU bound, simply trying to feed the GPU. This is the reason APIs like Vulkan exist, is to lower that overhead. If you're targeting Daydream, especially in the sort of this year time frame, our somewhat conservative recommendation is that you target 100 batches, 100 draw calls per eye, or about 200 batches per scene. You may find that for some games you can do more, for some apps you can do less. Engines, code bases, all that stuff varies. But to give you a very basic bottleneck, something to think about. Another way to actually reduce your batch count and run more efficiently generally is to bake everything that you can, right? Anything that's static that doesn't need to be computed dynamically, compute statically. So one great example is you want to combine local instances of static geometry. For example, there's 3 rocks on the ground there, and they're the same rock model, just rotated with one another. And if you just place each of them, that's 3 draw calls, 1 for each rock. But it's often for VR a good optimization to combine them into a single mesh. Now you can do that of course it's more polys, but you're saving batch count, and you're really not rendering much more. Like you still have to render all 3 rocks from the GPU's perspective, but the fact that you submit them once is a lot more efficient. And engines like Unreal and Unity have built-in optimizations. It's called static batching in Unity or actor merging in Unreal. And those are great ways to take content, author it in a normal way, but then crank down the number of batches. Light mapping, it looks fantastic. It takes some memory, but memory is much relatively cheaper in terms of like you have a lot of memory on these modern devices. So doing your doing high fidelity lighting calculations offline and baking them totally helps. One other really clever trick, if you have control of your camera, if you're in a fixed environment, is like past a certain distance, the stereo effect kind of goes away. And so if you can pre-render your backgrounds, render them into an ODS, a 360 stereo pano or mono pano, you can just like blit that right to the screen like a skybox. To the user, it will look just as real, and you'll save yourself a ton of time. One of the things you really, really want to be thoughtful about is the bus, the transfer, basically the circuitry that transfers data around the SoC. This is one of these things that you tend not to think about. Like, oh, there's memory and it's accessed randomly and it's fast. But actually one of the most energy consuming operations on the SoC is just reading and writing from main memory. And of course, when you're talking about like frame buffers that are 1080p, 1440p, that's like a lot of pixels to move around. Textures that are 4K by 4K, all of that is data that has to be shuttled back and forth, from main memory to the GPU and back again. So, some ways that you can manage the amount of traffic you're putting on the bus. The first one is you can actually tweak the off-screen render texture size. Remember I said when you that original function, they said, hey, give me the idealized off-screen target size. That's just a suggestion. You may find that for your particular application, you can run much smaller or much larger. So iterate with that. See what is the right balance of performance and fidelity. This is one of the biggest kind of constant optimizations you can make to your app. You always want to use compressed textures. So it's a lot of mobile developers are used to not compressing textures because maybe you don't have that many of them, you don't like the artifacts, but in 3D you want to compress things, and Daydream ready phones have all the latest ETC2, like really, really good texture compression, so take advantage of it. It will save you a tremendous amount of bus bandwidth and energy. And then the last thing you need to do is avoid full screen passes. A very common pattern on desktop and on console is you render your scene, and then you have another scene for shadow, or another pass for shadows, and another pass for bloom, and then depth of field, and then vignetting. On a phone, each of those full screen passes usually means reading from the main frame buffer and writing back to the main frame buffer, and all that's like millions of pixels back and forth across the bus. Instead, what you want to do is be very judicious and basically don't do full screen passes, but build them into your shaders to the extent you need to do them at all. So something like tone mapping, where maybe you're going from HDR down to LDR. Try to do that actually at the end of your pixel shader so that you only have to read and write to the frame buffer once. In general, though, you want to prefer the vertex shader to the pixel shader. Modern GPUs are homogeneous, whether they're processing verts or processing pixels, they don't matter too much. They will do whatever you tell them to do. But there's often 20x fewer vertices on screen than there are pixels on screen. And so if you can do something per vertex rather than per pixel, that's a 20x reduction in the amount of compute the GPU has to do. And so really, when you look at your shaders, get involved, understand what they're doing, and anything you can move to be, per vertex and interpolated, even if it's not quite as perfect, is probably a giant win in compute and in thermal. And in general, you can target, again, a little bit conservatively, about 100,000 verts per eye, or 200,000 verts per frame. And I should mention these budgets are assuming you're rendering at 60. If you're rendering at 30, which I'll talk about in a second, you've got a little bit more headroom. In fact, this is the other thing, because we have async reprojection, we will actually update the displays at 60 hertz, almost even if you're rendering much slower, we will keep updating the display to the best of our ability using async reprojection to correct for the user's head movement. So you actually, the best apps will look best when you also render at 60 hertz, but you can render at lower rates. You can render at 30 hertz, and what you'll see is you'll render a frame, and then we'll output 2 frames. And depending on the app you're building, that can look totally natural. The most key thing, no matter what frame rate you target, is to pick a frame rate and stick to it. Users can feel, if you're going from 20 to 50 to 30 to 40, users can feel that, and it'll feel unsettling. So stable frame rate, no matter what you do, is really key. I'd recommend for most developers, especially early on, try different things, evaluate, experiment. Don't lock in early on, at least not until you've done those experiments. If you are running at 30 hertz, it's really tempting to then spend 33 milliseconds on rendering. But actually, if you're running at 30 hertz, like you want to do that to save power, to save energy output. So actually, like use less than 33 milliseconds of compute. Let the phone cool down a bit, so use 20 milliseconds. It's still more than the 16 you get from 60 hertz rendering, but think of that as a power saving strategy, not just a way to spend twice as much time rendering. And lastly, like profile. One of the awesome things about Daydream is that it's on Android, and you get the benefits of the entire Android ecosystem for profiling. Android Studio's GPU profiling and debugging, Qualcomm's profilers, NVIDIA's Qualcomm, I guess, on initial Daydream hardware. And you also get like so much just out of the box. You get Unity and Unreal's profilers. If you write your own engines, all of that sort of stuff is really, really available and powerful. The last thing I want to mention is make it a habit. Be thoughtful about this in your team's workflow. I think it's natural for teams to think that they're going to just, okay, I'm going to do my app and they'll figure out performance later on. But that's brutal, super brutal, right? Like you're leaving a lot of hard work to the end of development. What you want to do in VR, because performance is critical, like make it part of your team culture. Make it something you do every day, twice a day. Have a performance cop every week that rotates and is looking at how things are running. Because if you don't stay on top of your performance and your thermal output, you're going to be in trouble later on in the game. Last thing I want to talk about is audio, which I think is kind of an unappreciated element of VR in general, and especially on smartphones. There's this quote I love from Martin O'Donnell, the composer of the original Halo series. He said, "Music makes you feel, sound makes it real." And like, there's no more true statement I've heard about audio design than that. You can create a tremendous amount of emotion and a tremendous amount of presence just through audio. And if you think about kind of like watts per immersion, like the amount you get from processing audio versus processing visuals, it's dramatically more efficient what you can do with audio. So as an example, think about rendering a tree, or you want to say like, well, there's a tree and the wind is blowing through it and rustling the leaves. Well, you can render, all the leaves on the tree and animate them as a way of saying, look, the wind is blowing through the tree. Or you can have a sound effect of wind rustling and a much simpler version of the tree. And users are going to find them both very plausible, right? In fact, they'll appreciate the sound more than just the pure visuals. And obviously, it's dramatically cheaper to render a simplified tree, perhaps not that simple, but a simplified tree with audio than it is to render one very complicated object. I mean, you can suggest objects that aren't there, things in the distance that, oh, I heard a wolf, they must be out there, without rendering any wolves at all. And since our goal really is to create presence, audio lets us do that really creatively, really efficiently. And again, as mobile developers, we tend to be like, the audio is the last thing we do. Like, make it the first thing you do, or the second after you integrate the API. Two other things to think about with audio. One is spatial audio. Some people call it binaural rendering. We have technologies, and we provide these with the Daydream SDK, that let you use headphones but get a sense of surround sound, like better than surround sound. We can give you a sense of sound above you and below you, all around you. It's really, really compelling. And it makes you feel it's much more believable than simple stereo panning, which is what you get by default. You also want to think about the way the environment affects the audio. If you imagine a conversation between two people, well, obviously that conversation would sound very different in a forest than it would sound in a spaceship. And our SDK has tools that let you actually specify the room that you're in, the size, the physical materials, and will process the audio in a way that's believable for that space. So we've covered a lot today. Really to wrap up, like all of this is how you create a sense of presence, how you get below that 20 milliseconds motion to photon latency. Like, we hope that will help you create luscious, beautiful, immersive, compelling VR experiences for Daydream. Thank you so much for making the time. We have tons of resources available online. There's the Google developer site, which has a subsection on how you can build your own Daydream developer kit. We have the NDK, where all of the code that we've talked about today comes from. And lastly, a giant section on spatial audio. I've linked here to our dev site page, but we also had a full session dedicated to spatial audio creation, technology. It was earlier today, but check it out online. It'll be posted to the main I/O channel later on. So thank you all very much. Thanks for being part of Daydream, and maybe you can make apps about flipping pancakes on the beach. So thank you.